We're here at Brookhaven National Lab with Dr. Peter Bond, the acting director. Dr. Bond, tell us about some of the science that's going on here.
Well, we have a whole variety of science, both the basic and applied research. We do basic research in physics, biology, medicine, chemistry. We've been getting the structure of the Lyme disease organism, which hopefully will help develop a vaccine to prevent Lyme disease. We, along with many other laboratories, are trying to sequence the human genome. We've been working on brown tide research to understand what it is that is the cause of brown tide in all the bays up and down the East Coast. And so we've been doing a whole variety of research on biological and environmental issues. Roughly 4,000 scientists come to the laboratory from around the world per year to do research on our facilities.
Okay. What made you decide to become a scientist?
Oh, that was a long time ago. The main thing is because it will always be enjoyable, you know. Science will never come to a finish. There's always something more wonderful out there to look for. We're very proud that we run for more than 6,000 hours in the year on 2 storage rings with nearly 80 experiments going on all the time, and we're providing 2/3 of the nation's synchrotron radiation experiments. On the scientific side, it's hard to say what you're most proud of because we have so many things going on. We have, for example, 4,000 papers in the scientific literature in the 1990s from our users. 4,000 in 250 journals. It's only 100 years since the only knowledge we had of nature came from light, visible light in our eyes. We've now expanded by a factor of 1 million in each direction the wavelength or the energy of the light. Infrared is 10,000 times longer wavelength, lower energy. Hard X-rays are 1 million times higher energy. And we work everywhere in between. And so we can match the scales of atoms, molecules, polymers, and large objects. We're actually in the business of producing light here for various science experiments.
Okay.
And by light, we mean all kinds of electromagnetic radiation, everything from infrared through to X-rays and gamma rays. We do spectroscopy, which means see how atomic and molecular systems absorb light. We do scattering and diffraction, which says how do atomic-sized systems scatter light. From that, you get their structure. It's impossible really to make an optimized machine from the infrared to X-rays. So in fact, we have 2 machines here. The small ring works best from the hard ultraviolet or soft X-rays through to the infrared, and the big machine works all the way from the hard ultraviolet through to the hard X-ray.
What are some of the things you're doing right now?
How do you get rid of the sulfur in coal? Sulfur's a big problem. And the answer is our people are looking at the microstructure of coal and see where the sulfur is, how it's bonded to the coal, and looking at processes by which you can get it out. And in biology, people want to know the structure of a very large molecule, which maybe has 100,000 atoms in it. And it happens to be a protein connected with Lyme disease, which of course is a local issue of some importance. And what they're trying to do here is they're working out the structure of the protein by scattering X-rays off the protein. Structures, like this blue thing here, it looks like just a sheet. That actually is a shorthand picture of a well-known structure which appears in many different proteins. And from the structure you can deduce its function, and by finding the right place to attack in here, you can, in principle, try to design drugs or treatments which inhibit its growth. And that's what people want to find. They want to find the atomic level structure, both from the point of view of the dynamics of the atoms, how the electrons in the atoms behave, that's spectroscopy, and where the atoms are. If you remember this diagram, the little storage ring has electrons in it at 800 million volts. That's it here. To give you a scale, this is the little one. That is the top of the storage ring, and if you look, see that white post coming down from the roof? If you look straight down, you can see a pale blue thing. That's one of the magnets that the storage ring is in, so that tells you exactly where the storage ring is.
Okay.
And then every bend in the storage ring gives out radiation, and these are beam lines which look towards the tangents to the ring. And one experiment is this whole lot you see here. That's just one experiment. And in the whole facility we have about 80 experiments at any one time. The funding for us to operate this facility is provided entirely by the Department of Energy, its Division of Basic Energy Sciences. The funding to build the beam lines, to operate them, comes not only from them, but also from companies around the country like Exxon, AT&T, IBM, It comes from other government labs, and so from other agencies like NIST in Washington, National Institute for Standards and Technology.
How long has the lab been here? I mean, give us a brief history.
Okay, the site of the laboratory is about 5,300 acres and has been occupied since the early 1900s, first by the Army during World War I, then by the Army during World War II. And following World War II, Brookhaven Lab was founded almost precisely 50 years ago to do basic research and to run major facilities for university researchers.
In 1958, it took Willy Higinbotham 2 or 3 days to design the very first video game. It took another month for him and 2 engineers to make the drawings and build a fully functional video tennis. In 1997, for the lab's 50th anniversary, it took over 6 man-months to replicate and reconstruct this historic machine. Okay, and something like this led to video arcades.
This is the granddaddy of them all, right here.
It started here with an open board with tubes instead of chips, but nevertheless an open board, and a couple of guys with nothing better to do. Is this your primitive joystick? Is that what this is?
Yeah, that's right. It's just a knob and a button. They were having the first visitors today, and Willy Higinbotham wanted to make a display that was interactive, so that it was more interesting to the people instead of just going and looking at a poster. He wanted them to be able to do something. We have the notes, Willy Higinbotham's notes, and in his notes, he says that there are errors in the drawing. Of course, we didn't know what the errors were in the drawing, so we had to figure out how, not only how this worked, but we had to figure out what the errors were in the wiring assignments on the drawing. In the spirit of the original game, we wired it up according to his instructions. So this is what it is. It's not fully faithful to the original because the original used an analog computer, and the analog computer used vacuum tubes. And of course, it's very difficult to find vacuum tubes these days. We have relays here that the original game used. Instead of using we put it together using just regular silicon chips. So we had to compromise there. Show how it works here, okay? And it should work. So ball's in your court. Ready? Go.
Would there ever be a situation where you couldn't be totally forthcoming with the public immediately?
Immediately is of course a concern because sometimes when you make a measurement, the first measurement you make may or may not be a correct one. There are instrumental errors, and when we want to confirm a result, it takes a day or two to confirm it, and then one goes public with it. But going public with a result which isn't confirmed is not helpful.
That's part of the basic scientific method, right? Is that things, once you do an experiment or measurement or something, it has to be reproducible in order to validate that it actually was accurate in the first place.
That's anyone who's done an experiment, I believe, at some time in their life thinks they've discovered something great, only to find that when they reproduce it, they made a mistake. And in fact, you may remember the days of cold fusion when there were a number of unreproducible results when people thought they had solved the world's energy crisis with something which I think was just an artifact. So it's very important that one have confirming measurements.
Do you think we'll ever get cold fusion?
No. It's a very exciting place to be and to look around and see what's happening. A lot of neat stuff is going on here, and I would just encourage people to come to the laboratory at the first opportunity.